All right. Okay, so today for geometry, we're starting a new chapter. And I'm going to get my tools here for a second. In our new chapter, we are doing chapter 5 and starting to talk about circles. Nope, sorry. So chapter 1 is called the Orthocenter, or the Circumcenter and the Orthocenter. Okay, so first of all, our objectives. We're going to apply the fact that a point lies on the perpendicular bisegment, or bisector, of a segment if and only if. I don't know if you remember this, but when we say if and only if, a lot of times we use IFF. It is equidistant from its endpoints. Okay, that's going to be helpful today. So a point lies on the perpendicular bisector of a segment if and only if it's equidistant. 2, we're going to identify a triangle's circumcenter. So we're going to identify the circumcenter and orthocenter and make some related applications. And 3, you can actually cross out. We're not going to do the construction. Okay, we're not. I was going to that, and I'm like, you know what? We're not going to worry about this. Construct a circumcenter. We're going to do some other different one. So first of all, then theorem 5.1 or 5.1.1. A point lies on the perpendicular bisector of a segment if and only if it is equidistant from its endpoints. Oh. So let's look at this diagram instead of that vocabulary. So we've got point P up here. So P lies on the perpendicular bisector. So do we get that this is a perpendicular bisector? Okay, this line. How do we know that's a perpendicular bisector to AB? What denotes that it's a perpendicular? What in the diagram tells us, hey, this is perpendicular. Hey, this is a right angle. Not that they're going through each other, more than that. The little angle box. Yeah, that little right angle box. Okay, that means that it's a right angle, but also that if it's a right angle, we know it has to be perpendicular. So that means both of those things. Okay, so P lies on this perpendicular bisector if and only if AP, so this AP is congruent to PB. That's the only way. Okay, they have to be equidistant. That's what that theorem says. A point lies or is on the perpendicular bisector if and only if it is equidistant. So that means those two sides are congruent. Okay, so I think the picture is much more helpful than the words there. Do we understand that though? So no matter if we put a different point, so let's say I put point Q here. What do I know about point Q? We don't know if it's a midpoint, but we do know that the distance from A to Q is equal to the distance from Q to B. Yes. Those are terrible lines. But yes, if a point is on the perpendicular bisector, it is equidistant. Like wherever the point is, doesn't matter. From the two vertexes there, is it going to be equidistant? Okay. Then for the next one, you should have your paper triangles. I want one paper triangle. Okay, so you should have had a paper triangle. I want you should cut it out. And we're going to follow the directions here to fold your paper triangle. All right, so it says fold one vertex. So take your paper triangle and fold one vertex onto another vertex. We're going to do it to all three vertexes. So see, I just took one vertex, I'm going to line it up on my other vertex, and then I crease it. And I crease it. It doesn't matter, because you're going to do this 3 times. It doesn't matter how you hold the triangle. Just take one vertex, fold it over to match your other vertex, and put a crease in it. Let's see. Yep. Okay. And then put a crease in it. And you have, in doing that, you have just created a perpendicular bisector, right? That's a perpendicular bisector. That is perpendicular. Yeah, it's perpendicular to the wherever you folded it. Right, but it's a perpendicular bisector, so it's perpendicular to this side.
Oh, I was holding it upside.
Right, that's good. Can I borrow yours? Because mine has extra creases in it. Okay, so on this one, so we have it, we creased it, right? Vertex to vertex, put a crease in it. This right here is the perpendicular bisector, because if we look, maybe if I take this, that's the line where we folded it. It's perpendicular. This is a right angle, isn't it? So when I open up, and maybe you want to trace it, I'm going to trace yours, Justice. That's a terrible pencil to use. All right, trace it and mark it in there. So if I trace that line, it's perpendicular to the base. And then you're going to do it again with another set of vertexes. Okay, so fold it, the crease. You've got another right angle right there, but you just made the perpendicular bisector to this line. Okay, so do that for all 3 of your lines. Lucas, you got yours? You think? Okay, so I'm gonna lay mine down here. I'm gonna trace my lines. Okay, so you might want to do that. Trace your lines, and then I fold the other vertexes together. Make a crease, open it up. I'm gonna trace that line. Because you could go corner to corner and line it up straight and make your crease. And then you should have one more. You should have 3 total. So line up, bring your vertexes together and crease it. I'm going to trace that. And there we go. Okay, so I'm going to put this back on here. So how many perpendicular bisectors did you just make? How did I get the last one?
Oh, it does look right. Okay,
Yeah, it does look right. You shouldn't have 6 because you only have 3 sides. You counted all the little lines when you traced them. So how many lines is that? One. Okay, hold on. One. Yours just looks like it's oh, because you stood yours up. Okay. Yep. I'm just checking to make sure you did it right. Yeah, it's kind of like a spider web. Good. Okay. Yep. All right. So how many perpendicular bisectors did you make? How many times did you fold it? 3. So you made 3 perpendicular bisectors. Okay, I'm going to stand this up actually, so maybe it'll help us think about that too. So there should be a perpendicular bisector for each side, okay, that you made. Now, so you have 3 perpendicular bisectors. I marked where they were perpendicular, which side they were perpendicular to. So that also helps me count because I have 1, 2, 3. Now, when you folded every vertex, you got a perpendicular bisector of each side, which we said was 3 of them. But do you notice how they intersect? You should have a point of intersection. This is called the circumcenter. So label that circumcenter, or you can label it C. And maybe on the back you want to write circumcenter. You could use it because we're going to tape these into your notes. Well, so circum comes from circumference, like a circle. Okay, so C-I-R-C-U-M, circumcenter. All right, so that is a circumcenter. Now we have the circumcenter theorem. All right, so this theorem says the perpendicular bisectors of the sides of a triangle are concurrent. Okay, that just means intersecting at the circumcenter, the point that is equidistant from its vertices. So this point is equidistant from all of the vertices. Hold on. Okay, so the dash lines over here, the dash lines are perpendicular bisectors, and point C is the circumcenter here. Do what? Now, this last part, it says this is the point that is equidistant from its vertices. What does that mean? Actually, I'm going to change colors here. Okay, I want you to take your straight edge. I think I gave you each a protractor for a straight edge. Maybe a different color pin even or something if you have it. Okay, equidistant from its vertices. That means, and maybe you just want to watch, from this vertex to this vertex is the same as from this, the circumcenter, to this vertex. And from the circumcenter to this vertex. All of these are congruent. They're equidistant. That's the point. That is the center of your triangle. That's pretty cool. That the circumcenter is the center of your triangle. Now, with that being said, all right, I want you to take your compass. We're going to draw a circle. I set my, does everybody have a compass? I set an extra one out here and now I can't find it. The metal one? Nope. Like this. You're good. It was the, oh, here it is. I put it on my desk. All right. So, I want you to check that out. So I want you to take this, measure it out to the vertex, one of the vertexes. I'm going to go to G. And my drawings aren't perfect, right? You know this, right? I don't make instructions on my notes. I make drawings. But check that out. So if I measure out from the center, my circumcenter, to G, and I'm going to try to make a triangle, or I'm going to make a circle. And hey, look, it intersected my vertex because it's equidistant. Hey, look, it intersected my circle because it's equidistant. How cool is that? Isn't that awesome? So we just proved it as well. And this is called a circumscribed circle because we are able to scribe a circle around the triangle that touches all of the vertexes. So we're going to do the same thing. Okay, we're going to take this triangle with the circumcenter marked. Looks different though. It's on, this is a right triangle, and so the circumcenter is on the line instead of in the middle. Okay, we're going to use the circumcenter as the center. Okay, so that's the center. So I need to measure out to my other sides, one of my other vertexes, or my vertex. And we're going to draw around a circle around the triangle. And let's see if it touches all of the vertexes or vertices. Ah, I got mine to touch in. I can't get my paper to turn now. I'm up against the wall. It doesn't want to turn on me. Mine worked. Did yours work? No. Yeah, you don't seem very excited. Oh, that the circles intersect? I'm sorry. Lucas, did you get yours to work? Awesome. Okay, so then I want you to take and make an arrow. The circumcised circle, point it to each of those. Okay, because that's when we use that circumcenter and we use that as the center, we can make a circle that will touch all three of the vertices. So I kind of just answered the what do you notice for you. Is that the circle touches all three vertices. So we use the circumcenter to make a circumscribed circle. Like your papers, I want you to know, should look really geeky and nerdy right now. With triangles, with lines, and all the things, and then a circle around that. It's really nerdy. Okay. Now, if we flip over, we have a definition for this lovely circumscribed circle. So any circle containing all of a polygon's vertices. So it doesn't have to be a triangle, okay? It's called, and it might say it's circumscribed around. But a circumscribed circle is any circle that contains all of the polygons of a vertices. So if I had a circle and then I had a pentagon inside of it that looked like this. This is a circumscribed circle because each of the vertexes of my pentagon is on the circle. Does that make sense? Okay. But it could be any polygon at all. But the center is the circumcenter in a triangle. That's also cool. All right. Now, changing gears a little bit. Another point of concurrency. What was concurrency? Earlier I said concurrent meant, it's not on your notes, but it's intersection. So another point of intersection is determined by your triangle's altitudes. All right, so which we haven't talked about altitudes. Earlier we talked about perpendicular bisectors, but we haven't talked about altitudes. So the altitude of a triangle is a segment that extends from a vertex and is perpendicular to the opposite side. Okay, so it comes from a vertex and it's perpendicular to this side. So it can be in the triangle, it can be a side of the triangle in a right triangle, or it can be outside the triangle. Like this one, it's extended outside. It's this obtuse scalene, and so our altitude is there. So where can the altitude be in a triangle? Anywhere. So it can be in, it can be a side, it can be outside. Okay, any of those can be where the altitude lies. All right, now you need your other triangle. Okay, we're going to do some more paper folding. But this time we're going to fold it to get altitudes. Okay, so you take your triangle. Okay, so take your paper triangle, fold aside so that the sides align. Okay, so you want the bottom of your sides to align, but the crease has to run through the vertex. Mine's a little off right here. So you want to fold it where the sides align, like here, but it has to run through the vertex. I actually lick my fingers because it's kind of hard to do, so I can get a better grip on my paper to kind of roll it in place. Okay, and get it to go through the vertex. It's a little harder than it sounds sometimes. And we're not, see that one I got too much. We're not really going for perfection, but as close to perfection as we can get, right? Okay. And so I'm going to trace that line. So it goes through the vertex and it's perpendicular. So that's an altitude. Okay, and you're going to do that with all three sides. Close enough, right? That's okay if there's a close enough. So you want to make sure that your sides here are even, they're together, they're aligned. That's what makes it perpendicular, and then it has to go through the vertex. We're folding the vertex. Okay, open it up. Trace that line up through your vertex pretty close. Mark the perpendicular side, and then do your last one. So fold it through the vertex, put your crease in it, open it up, and mark it. Okay, so you should have, I'll set it here. All right, and then we get another point of another concurrent point. This one's name is O. Though. All right, Lucas, you got yours? All right, let's check it out. Very nice. Okay. Good. Okay. So here's the question. We folded it different. Do these look the same? Our O and our C? No, they do not. Okay. The O, what we just did here, okay, every time we folded it, we made a, okay, so when we folded the side, increased it, ran along, we made an altitude. So how many altitudes did we fold? How many altitudes? On the last triangle we did here, how many altitudes did we fold? We folded it 1, 2, 3 times. So how many altitudes did we get? How many times did we fold it? Like this is an altitude. We got 3, right? We folded it and we got 1 altitude. Like the altitude. The lines total. Like this, extending from O is just a byproduct that we need. But from the base to the vertex is 1 altitude. Okay. All right. So that's the thing. Like this is a perpendicular bisector. This is an altitude. They're both perpendicular, are they not? Yeah, but this one cut this in half. So it means this side over here is the same as this side over here. That's not the case with this one. So see, these are perpendicular bisectors versus altitudes. Very similar. Okay, but when we have this point of intersection from our altitudes, it is called the orthocenter, which is why we name this point O. Okay, or it's called the orthocenter. And so you might say O. So the theorem for that is the lines that contain the altitudes of a triangle are concurrent or intersecting at the orthocenter. Okay, but it's the lines that contain the altitudes. Circumcenter is the perpendicular bisectors. Altitudes create the orthocenter. It might help for you to remember ortho means, like we talk about orthodontist, right? But ortho means straight, which may not be so helpful, but upright. It's the connection, it's the upright connection from the base of the triangle all the way to your vertex. That might help you remember ortho, as it goes back to altitude. An altitude is like a mountain, right? Like if you want to get to the peak of the mountain, you want to know the altitude to get there. So from the base to the peak is your altitude. Okay, those might help you remember those terms. All right, so you have two very different things here. The circumcenter and the orthocenter. Do you think we can make a circle with this, with an orthocenter? That's going to touch all the corners or all the vertices? No, we're not. Okay, the orthocenter is not equally distant. It is not. Okay, so flip over to your next set of notes. Hey. Oh, nice. Okay, so Lucas, these will be online if you need to, so you can finish them tonight. Okay. All right, so let's look at these. Identify each as an orthocenter or circumcenter and why. So let's look at this first one. Which one do we think it is? Oh, you're coming back? Oh, okay. You're just stepping out for a minute. Which ones? So remember the orthocenter. What does the orthocenter have?
Oh, we're just doing all of them, or we're just picking up?
Yeah, no, we're doing all of them. We're gonna go one by one.
Okay, well that one's the
This one's the circumcenter. Yeah. The first one. Why do you say that?
Because it's not in the straight up like the ortho one. Is that wrong?
It's not straight up. What do you mean?
See, for this one, you said that it had to be
Through the vertex?
Yeah.
Okay, good. So this is a circumcenter. So we know it's not through the vertex. I'll say vertices here. So these lines do not go through the vertex, which means these lines are perpendicular bisectors, which is also shown here because it shows us this is cut here. Those are those are equal. The perpendicular bisector cuts that segment into two equal parts. And so this one is congruent to this one. And then this side, or that piece, is congruent to this piece. So perfect. This one is a circumcenter. Woohoo! All right, how about the next one? The orthocenter, okay, because this one goes, it's perpendicular, but it goes through the vertex. So this is an orthocenter. So it's through the vertex, or through vertices, which means what are those lines called? They're not perpendicular bisectors, but altitudes. Good. So these are altitudes. Okay, how about the next one? Well, you have a great basis. You gave great reasons.
It's not straight from the vertex like the orthocenter, but then I don't know.
You mean this one doesn't look like it's straight through? Yeah. It's true. It doesn't look quite straight, but we're going to assume that it is because they screwed us up with this, all the little dots. But
the other one is, so in the corner.
Yeah, okay. So this one is an orthocenter again because it goes through the vertex, right? It goes through each of those vertices. All right, so this one's an orthocenter. Woohoo! How about the next one?
That is a orthocenter.
Going back and forth between orthocenter and circumcenter.
That's why the other. You can pick which one it is.
Actually, you can pick because it's both.
Uh-uh.
Mm-hmm. Yep, it's an equilateral triangle. So that is a thing. Sometimes the orthocenter and the circumcenter are the same. Sometimes it's going to be in the center, in this triangle. Sometimes it's on the side of the triangle. Sometimes it's outside the triangle. But in this case, it is. This one is displayed as a circumcenter because, let's look here. We did this on our first one.
See, that's what I was confused about, but then it went straight through the vertex.
Yeah, so it's saying that these are equidistant, right? The distance from G here is equidistant. So this one is trying to show you that it's a circumcenter because of the equidistant G. Let's say G is equidistant from vertices A, B, and C. So it's trying to show you that it's a circumcenter, but it does throw you off because it also goes through the vertices, right? Each of those is perpendicular and goes through the vertices. So it's also an orthocenter. Okay, because it's through the vertices. So is that the same for this one up here? Kind of looks like it, but they didn't show it to us. They didn't prove it, so we can't make that assumption. But yes, so in this case, the circumcenter and the orthocenter are the same. Woo woo! Pretty cool. Way to notice. Okay. Good reasoning skills, though. Very good reasoning for that. All right, then we have one problem to go. We just have one example today. Okay. So, clear the page. All right, example 1. Find the coordinates of the triangle's orthocenter. Is what it says to do. Okay, so we want the orthocenter, so we need the altitudes, right? Okay, so first of all, the easiest altitude to find is going to be the vertical one, because altitude goes through the vertex. So the easiest one to find is going to be this one. All right, so we need to, it says, write an equation for the vertical line. Well, what is that equation? A vertical line, we always say, is where, what value is this? Our x or y value? X. So we're going to say x equals what number? We came over. Here's 0. We went over 1, 2. So x equals 2. That's our line. That's the equation for our vertical line. All right, 2. Write an equation for altitude from B. Okay. You could do from A. It doesn't matter. So from B, but we can see this point of intersection right here. Okay, so from here to here, we want to write that equation for this altitude. So to write that equation, what do we think? How will we find the slope if we know this is perpendicular? Let's start there. How will we find the slope? Rise over run. Okay. That might be a little harder here. Or do you think you can get that? What is it? Oh, no, you can probably do that. What is the slope? We rise. Wait, are you starting? I was going to, it doesn't matter. Which point do you want to start at?
B.
At point B? Okay, so from point B, we rise 2. Ooh, not positive 4. Because we went back. Okay, so our slope is 2 over negative 4, which reduces to be negative, what's 2/4 reduced to be? 1/2. Awesome. Okay. So there's our slope for our equation. We know, right, that to write an equation, it's y equals mx plus b. So, because we're wanting to write an equation for the altitude from B. So what do you think now? Do we know B, the intersection? Where are you looking at for the intersection?
That's not that point.
Can you tell what that point is?
No.
No, so we don't know B. But we do know it's there, but we can use one of the other points, right? We can write a line. If we know the slope and another point that's on the line, we can write the equation. So we could take this point, right, which is 4, 0. Okay, and we can plug that in. Remember, we just need the slope and the point, and we can use point slope form, or we can put it in here. So our y is 0. Our slope is negative 1/2. Our x is 4, and then plus b, and we can solve, right? Yeah. So 0 equals, what's negative 1/2 times 4?
I don't know.
Okay, well, a negative times a positive is a negative. What's half of 4? 2. You do know. Okay, plus b. All right, so how are we going to get b by itself? We have,
I know this. I just don't know.
well, we have a negative b, so we need to, or a negative 2, so we need to add 2. So 2 equals b. All right.
Is that it? Or do you need to...
Nope. Okay, well then I have solved the system of equations. I don't know about the system of equations, because we just find the coordinate. Oh, okay. It's not really solving, I mean it is, but we haven't talked about solving a system yet. Well, because you guys talked about it last year. Okay, but anyway, so then what's our equation? Y equals, what was our slope? Negative 1/2 x plus, what was our b? 2. All right, so here's our equation. And it says solve the system of equations to find the intersection of the altitudes. All right, so now we want to know where they intersect. That point right there, huh? Which, okay, we know the intersection is, our x value is 2, right? Okay, so we know our x has to equal 2, which is why we wrote this line here. So we are, I forgot. Okay, so we are putting this into here. Yep. We did? Okay, so we're going to have y equals negative 1/2 times 2 plus 2, right? Okay, so y equals, what's negative 1/2 times 2? It is a negative. And then half of 2? 1. Okay, and plus 2? Negative 1 plus 2 is 1. So y is 1. All right. And we know our x is 2. So it's 2, 1 is 0.0 or 0.0. The orthocenter is at 2, 1. So our drawing doesn't look like it's right there, but that is exactly where it should be. Okay, our drawing is off. Or I mean slightly, because it didn't go quite through the line, so we couldn't pick it out. But also, like, we shouldn't, because I kind of picked like, oh, well, this kind of looks like maybe the midpoint, even though, okay, but it is a matter of writing the equation of the vertical line, write an equation for the altitude. So we find the slope. Okay, we wrote an equation for that altitude because it included, we found the slope of where it would enter, of the line here, and then where it would intersect.
What do I do with these little triangles?
I'm going to give you some tape. Tape your triangles in there so you can go back and reference them. All right, then that's it for today.